welcome to the area of vibration and air oscillating lecture series. And today we are going to see about the what is the damping, critical damping constant and the damping ratio. This is a variety of the last class. Last time we discussed about the Normal differential equation for the damped free vibration. There we have derived the solution as x equal to a1 e power of u1t plus a2 e power of u2t. So this will be a a1 e power of minus c by 2m plus root of c by 2m the whole square minus k by m and plus a2 e power of minus c by 2m minus root of c by 2m the whole square minus k by m. So this is what we have derived in the last class. Today we are going to see what is the critical damping. So critical damping will happen mathematically. The term from this equation c by 2m the whole square is equal to k by m becomes 0. Then this time this damping will react as c will react as the critical damping. So by replacing c equal to cc by 2m the whole square minus k by m is equal to 0 and cc will be root of k by m into 2m. So this is the critical damping, and this critical damping we can also write written as cc is equal to 2m root of k by m. This k by m we can write it as omega n. This is the for a spin mass system. This is the natural frequency for the system. And coming to the damping ratio is zeta is a ratio between damping coefficient to the critical damping. That is c by cc. This is the damping coefficient. So this makes the sense that how this element can be replaced as in terms of damping ratio, and the system can be observed how it is reacting either the underdamping, overdamping, or critical damping based on the dampers which we are using in the system, mechanical system. Now we can replace this in here as a damping coefficient. Damping coefficient we can replace as cc as this damping ratio. We can rewrite this equation in terms of, let us take from this entire equation we can rewrite this c by 2m as c by cc is cc by 2m. So c by cc is damping ratio zeta, and this c by 2m, cc by 2m will be root of that is omega. Let us take this is the omega. So we can replace this c by 2m in this equation, this entire equation in the form of damping ratio. Let us substitute here. So x will be a1 e power of, so the common term of the entire term will be minus zeta omega plus root of zeta and the omega the whole square minus this term will be root of k by will be omega. So we will have the one more term is omega square. So again for another term a2 e power minus zeta omega minus root of zeta omega whole square minus omega square. So the common term from this solution will be omega square is there inside the root. So here are the same thing. So we can rewrite this equation in terms of damping ratio as well as the frequency ratio. Then this equation will become x equal to a1 e power minus omega, and we will get zeta, that's damping ratio, plus this is here we will take minus here. So plus root of zeta square minus 1. So this makes the sense that damping ratio is dominating under the 1. So This one we are getting one solution here, and A2 will be e power omega minus zeta minus root of zeta square minus 1. So from this entire solution, if you make changes in the damping ratio, like this, if you have some damping ratio is 1 means the 10 will 0, 1 minus 1 0, then you get 1 e power again omega. Again, this is also a to e power omega. So if you get this under critical condition. So let us take three possibilities. Omega, I mean zeta may be 1, omega may be less than 1, zeta may be greater than 1. This three condition gives whether a system is under or over critical damp, that we will see in the next class.